So far we've learned about Boyle's law, Charles' law, and Gay-Lussac's law, which describe the relationships between temperature, volume, and pressure. We've discussed how they come together to form the combined gas law, which works well when you're comparing a changing pressure, or changing volume, or changing temperature, assuming that you haven't gained or lost any moles of gas. Now, when describing a gas under static conditions, or not changing conditions, we can use the ideal gas law. And the ideal gas law shows that the pressure times the volume is equal to the number of moles times a constant that we're going to calculate in a minute, and times the temperature. Now this equation, anytime you have two variables next to each other in an equation, it tells you that they're an inverse relationship. Like you know pressure and volume is an inverse relationship from Boyle's law. You can also see that the number of moles is on the opposite side of volume, and they have a direct relationship. So the more moles of gas, the more space it's going to want to take up. Or the more pressure is going to, if it's a constant volume, the more pressure that's going to be in there. Like if you're inflating a basketball and you keep putting air in. And it also shows you the direct relationship between temperature and volume. When you heat up a gas, it's going to expand. Or if you heat it up, the particles start moving faster and colliding with the walls more frequently and with more force and exerting more pressure. So there's a lot that can be found in here. What we're going to do is take our knowledge that 1 mole of any gas at STP occupies 22.4 liters. So STP stands for standard temperature and pressure, which is 1 atmosphere and 273 Kelvin. Now the pressure can be described in a bunch of different ways, and we'll get to that in a minute, but we're going to use atmospheres for right now. So what we do is we write out our equation, PIV-NERT, Pp equals nRT, and we write down the variables we have. Pressure of 1 atmosphere, volume of 22.4 liters, 1 mole of gas at 273 Kelvin. And what we're going to do is, since we're solving for R, we're going to rearrange our equation to be PV over NT, and then we plug in our values. And what we'll find is that our R value, and this is a constant, so no matter how much gas you have, what the temperature is, what volume it's taking up, or what pressure it's at, that value remains constant, is 0.0821 atmospheres liters per mole Kelvin. Now, this number, I just said it's a constant, but it changes depending on how you're describing the pressure. If you're using kilopascals and not 1 atmosphere here, you're going to get a different value. In fact, that's the problem I want you to do right now. Figure out what R would be if you were describing 1 atmosphere in terms of kilopascals.